Okay, hi everyone. This is my lecture 9, which is about all things related to light. This is such an important topic. First of all, it's the culmination of a bunch of things that we've talked about so far, electricity and magnetism, but it's such a relevant topic to our lives. So much technology and, you know, important aspects of our lives are related to light. So the first part of this lecture is about, discussing what electromagnetic waves are, how we describe their properties, how they're created and how they're detected, how they interact with matter. And then the second part of the lecture is really about how we understand how light interacts with lenses and mirrors to create images, right? And so this explains a lot of things that we use in our day-to-day lives, like, not to mention how we see with our eyes, but also how cameras work, how telescopes and microscopes work, how a curved mirror works. So lots of really important topics to discuss and really beautiful topics, right? So this is maybe an image that we've seen all our lives. It's what happens when you send a beam of light through a prism. It breaks up that light into a rainbow, right? So we'll be discussing even the physics of rainbows. Okay, so let's get started. So before we even discuss what an electromagnetic wave is, we should discuss some properties that are, universal to all waves. So usually when I talk about waves, I first do a review of oscillations, right? So an oscillation is a disturbance in time that is somewhat periodic, right? A wave would be a disturbance in both time and space, right? And so we think of a wave as something that transfers energy and thereby transferring information, but it does not transfer any material or substance away from the source, right? So here we have, an image of maybe a wave on a slinky. It's moving left to right. Or if you want to think about a wave in a crowd where people are standing up, nothing is moving, no material substance is moving, but energy and information is moving. Okay, so there's two main categories of waves. For a transverse wave, the disturbance would be perpendicular to the direction of propagation, right? So this would be kind of like the wave in a crowd where things are moving up and down, but the direction of the wave is perpendicular to the direction of the disturbance, right? So this would be, a woman moving, in this picture, a slinky up and down and creating a periodic wave. A longitudinal wave, on the other hand, is a disturbance that is parallel to the direction of propagation, right? So in this example, instead of moving the slinky up and down, she's moving it in and out, and that's creating a periodic disturbance in the direction of motion, right? And so this creates, parts of the slinky that are condensed and parts of the slinky that are stretched out, and this is what gets transferred along the length of the slinky, right? So you can definitely talk about a speed of that wave and how it moves left to right. So this, example of a longitudinal wave, it's really similar to our understanding of what sound waves are. So sound waves are periodic longitudinal disturbances in air pressure, right? So you can think of any time you hear a sound, what's creating that sound is some sort of periodic disturbance in the pressure. So there are parts where the air molecules are very dense and parts where the air molecules are stretched apart. Right? So this would be, a plot of air pressure as a function of distance or as a function of time. Okay, so here's our first picture of an electromagnetic wave. So notice that it has an electric field E that's plotted in pink, a magnetic field B that's plotted in blue. And really what is changing, what's the disturbance, is the magnitude of the electric field and the magnitude of the magnetic field. But notice that they are always perpendicular to each other, right? So the electric field is actually moving in the XY plane. The magnetic field is moving in the XZ plane. And I shouldn't really say that it's moving, it's actually just changing its magnitude and direction, right? So sometimes it points up and sometimes it points down, the electric field, and then the magnetic field goes in and out in the XZ direction. But the direction of propagation of this electromagnetic wave, right, is in the positive X direction. So it's traveling along the positive X direction. The electric field is moving up and down, the magnetic field is in and out, right? And they're always 90 degrees apart from each other. Okay, so this is a very obvious question. What kind of wave is an electromagnetic wave? It's a transverse wave, right? So it's a transverse disturbance where the disturbance is always perpendicular to the direction of motion. Okay. Okay, so we will always refer to the word light as a synonym of electromagnetic waves, right? So there's, a conventional description of what light is the stuff that we see. Scientifically, we would refer to it as visible light. But electromagnetic waves are actually more universal than just visible light. But whenever you hear the word light, it will be in reference to all electromagnetic waves. So one thing that's very disturbing and kind of interesting about light is that it is both a wave and a particle, right? I do have more information about that coming up. Right, we have perpendicularly oscillating electric and magnetic fields. These fields are oscillating with the same frequency and the same phase, right? So notice how when the electric field is small, the magnetic field is small, and vice versa. They go through a maximum and minimum at the same time. It always propagates in a straight line, right? So this electromagnetic wave always goes in a straight line. As long as it's propagating in a vacuum, it will continue undisturbed. It is also the fastest thing in the universe, right? So this is the most important constant in science, maybe. It's the speed limit, right? So there's nothing that can go, no transfer of energy or information that can go faster than the speed of light. And it's good to just know that it's 3 times 10 to the 8th meters per second. We're going to use that constant a lot in lecture 10, right, when we get to relativity. Another thing to know is that at all points on this wave, the magnitude of the electric field is going to be equal to the magnitude of the magnetic field times c, right? So now we know, a new way of relating constants, right? Because the not constants, but units. So the units for electric field are, volts per meter. The units for magnetic field are Tesla, right? How do we relate the magnitudes of these two things that up until now we thought had not that much in common? It turns out that if you multiply Teslas by meters per second, you should get the units for electric field. So at all points on this wave, the electric field is equal to C times the magnetic field. Okay, so we should probably discuss at this point what is a wavelength, right? Because how do we describe waves in general? So a wavelength would be very equivalent to a period in terms of that the period is the time for an oscillation to go from peak to peak. Likewise, a wavelength is the distance between peaks on a wave, right? So there's kind of two main pictures of how to describe a wave. One would be, how is that disturbance changing in time? How is that disturbance changing in space, right? So you could think of this as a picture of a wave, a photograph of a wave, right? So it's frozen in time. The distance from peak to peak here would be called the wavelength, right? And we want to use the Greek letter lambda to represent wavelength. So here, these are representations of the two main pictures of a wave. So here I have a plot of amplitude as a function of time. Here I have a plot of amplitude as a function of space, right? So the time to go from peak to peak on this graph would be giving me the period t. Here, the space to go from peak to peak on my disturbance as a function of space, that's wavelength, right? So the relationship between period and angular frequency is period is 2 pi over angular frequency. Likewise, you can make a similar description of wavelength as 2 pi divided by k. And in this case, k is often called the wave number. We're not going to use this variable in this class, but I did want to mention it in case it comes up somewhere else. Right? So how would you write out a formula for the the equation of a wave? How could you describe it? So it would be some sort of sinusoidal function. 2 pi over lambda, right, would be able to give me sort of a frequency in terms of space. 2 pi over t would give me a frequency in terms of time, right? So it gives me what this argument gives me is that anytime I go from t equals 0 to t equal to 1 period, I've only changed the argument of this cosine by 2 pi, right? And we know that cosine is periodic every time you go through 2 pi radians. Okay, one last thing to discuss is how would you specify a wave moving to the right versus to the left? In this case, it would just be this sign, right? So if this sign is negative, this would represent a wave moving to the right, right? And how do I know that? So here I have a bunch of pictures of a wave. Every picture is a quarter period after the one before it, right? So we can think of this as kind of representing a movie. And this point on the wave is moving left to right, right? So it's gradually moving to the right as I move forward in time, right? So if I want this point to represent the same angle or the same argument of this cosine function, and I want the position to gradually increase, right? That would mean that I would need a negative sign here in order to make sure that this total argument is a constant, right? So as t gets bigger, x gets bigger, and therefore I need a minus sign here. If I wanted a wave traveling to the left, I would need actually a plus sign here. Okay, so not really an important fact to know, but I did want to show what the equation for a traveling wave looks like. Right? And what is a really important and useful formula to know is how do you describe the speed of a wave? So this is maybe the most useful and simple formula about waves. It tells you that the speed of a wave is equal to the wavelength times the frequency, right? Or another way to write this, right? Because frequency f is the inverse of the period, you could write this as wavelength divided by period. So dimensionally, we know that this makes sense because wavelength has units of meters, period has units of seconds, so we want speed to be in units of meters per second, right? But this is, a formula that is universal to all waves, is that the speed is equal to wavelength times frequency. Okay. So here's a couple of example problems about calculating wave speed, wavelength, and period. So here you have a picture of a disturbance as a function of space, and here you have a picture of a disturbance as a function of time. So I'm going to give you guys a second to think about this problem and figure out what the right answer is. Okay, so hopefully if you wanted to answer this question, you paused the slides. Okay, so let's talk about how would we calculate wavelength. So here wavelength would be the distance to go through a full cycle or to go from peak to peak, right? Either way, I can tell that the wavelength here is 4 meters, right? How would I figure out what is the period, right? So again, I need to go through a full cycle of oscillation or need to go from peak to peak, right? Either way, I can tell that the period here is half a second. Right? So if I need to divide wavelength, which is 4 meters, divided by period, which is half a second, I should be able to get that the speed is 8 meters per second. Let's see if I was right. Good. Okay, so let's try another example. It says, what is the frequency of this traveling wave? So here you have a little bit different information. You have to find the frequency. Okay, so go ahead and pause, try to answer this question. Okay, if you're coming back. So here again, we're going to use this formula for wave speed is wavelength times frequency. So here I know the speed is 50. What would be the wavelength? So here wavelength would be 10 meters, roughly. So if I need frequency to be wavelength, or speed divided by wavelength. So I would expect it to be 5 hertz. Cool. Okay, so let's continue. Okay, so now that we're familiar with, some properties of waves in general, let's discuss what the electromagnetic spectrum is. Okay, so probably you've all seen a picture like this before. I'm wondering where I can put my head so that it's not in the way. Here, I'll just move over here. Okay, so most importantly, right, we can categorize electromagnetic waves by their wavelength. The longest wavelengths on this spectrum are radio waves, and then we have microwaves, infrared, visible, ultraviolet, X-ray, and gamma ray. Right, so as we move left to right, we have smaller and smaller wavelengths. We have radio wavelengths being approximately the size of buildings. We have microwaves about the size of people and animals. Infrared wavelengths are approximately the size of a needle point. And then we have visible light as the size of microorganisms. Ultraviolet light is the size of molecules. X-rays are the size of atoms, and gamma rays are the size of atomic nuclei, right? So knowing the relative size of electromagnetic waves is important because that will determine what types of matter are most impacted by those waves, right? So I do want to discuss that a little bit more. Here we also see in the visible spectrum, it's showing us that we're going from red to orange, yellow, green, blue, right? So this is showing us actually the spectrum of light. But once we get to ultraviolet light, these are not visible with the human eye, right? So, and then infrared light is not visible to the human eye. Another thing that's demonstrated here is the black body spectrum. So it's actually telling you the corresponding temperature that an object of that temperature will glow at a color represented by this scale here, right? Okay, so I have some other simulations that I want to show. So let me just skip to let me see here. No, that's not what I wanted to show. Hold on. It's not showing me. That's not what I wanted. Okay, I'm gonna pause and try to figure. Okay, I'm back. So I was trying to show actually these simulators, the PhET simulators, because they are really fun. But for some reason, I wasn't able to transition to those windows. So I would just recommend that you check them out. They're all linked to on the Blackboard page. Okay, so let's continue with the slides. So this is just another, picture of the electromagnetic spectrum. So you can see side by side the frequency range for each type of wave and also the wavelength range. Okay. Okay, so again, we can relate frequency and wavelength by using this formula, except, for an electromagnetic wave in a vacuum, we have a very precise definition for the speed, right? So the speed of an electromagnetic wave in a vacuum is going to be 3 times 10 to the 8, right? There we go. Sorry about that. Okay. So how could I calculate frequency? I would do 3 times 10 to the 8 divide by this wavelength of 300. So this is 300 times 10 to the 2. So I would expect the right answer to be 10 to the 8 divided by 10 to the 2. So I think the right answer is C. Right? Light wave A has twice the frequency of light wave B. The wavelength of light wave A is half the wavelength of light wave B. right? Because wavelength and frequency are inversely proportional to each other. Okay. Let's try the next thing. So now that we know a little bit about what electromagnetic waves are, we can talk about how they're created and also how they're detected, right? So this has a very broad range of relevance, and many different kinds of electromagnetic waves are created in different ways. But let's talk about what the general principle is of creating an electromagnetic wave. So these animations are meant to represent a charge, right? So the red dot represents a charge. We know, from the beginning of the semester that the electric field around a charge either points, radially inward or radially outward, depending on whether the charge is a positive charge or a negative charge. But here we're considering what happens if an electric charge accelerates, right? So first of all, what happens when a charge moves? We know that a moving charge will generate a magnetic field, right? So we have an electric field generated by a charge existing, a magnetic field generated when a charge is moving. What happens when a charge gets a kick, right? We would expect something like this, right? So some sort of wave emanating outwards in all directions, right? So it triggers a wave because of this acceleration of the charge. Here on the right, a similar demonstration, except here I have a charge that's oscillating. So it's oscillating up and down. It's generating a periodic electric field that's changing. It's also generating a perpendicular magnetic field, right? So here's maybe another important thing to consider is that a lot of times when we need to generate electromagnetic waves that are very, very short wavelength, those energies relate to the transition energies of an atom. So here, how do we create X-rays? We need to bombard a metal with high-speed electrons. These electrons can ionize the atom, right? So now we have an ionized atom because this electron got kicked out of the atom. But then eventually this ionized atom accepts a new electron, and when that happens, the atom needs to emit a photon of light that has the same energy as the energy that is gained by the electron or lost by the electron when it falls into the potential energy of the atom, right? So a really important aspect of understanding how electromagnetic waves interact with matter is knowing that basically electronic transitions in an atom are associated with very well-defined energy levels, energy transitions, and that any time you have an atom that is relaxing to a lower energy, that will be emitting an electromagnetic wave. Anytime that you have the opposite scenario of an atom sending an electron to a higher energy level, that would be absorbing an electromagnetic wave, right? Okay, here's the birth of how radio waves were created. So here I have an LC circuit, right? So in the previous lecture, I discussed how LC circuits oscillate as a function of time. It's connected to another part of the circuit via transformer. So this could be maybe an amplifying transformer that amplifies the voltage in this circuit. And it's connected to something that is a spark gap. So this would be maybe a very tiny gap in a circuit that would cause an electron to very rapidly jump from one end of the gap to the other. That acceleration would generate an electromagnetic wave, right? And that electromagnetic wave could be picked up by an antenna or a receiver, right? Here's maybe a little bit more detailed picture of that same process. And here it's showing that, yes, we know that an LC circuit oscillates in time, but you could think of the capacitor end of that circuit could become an antenna that creates an electromagnetic wave, right? So it's generating electric fields, and then basically what's happening is the electrons are moving up and down in this antenna, generating an electric field. But we also know that a current will generate a magnetic field, using right-hand rule number 2. That magnetic field is perpendicular to the electric field, and this is how we generate an electromagnetic wave. Okay, here's some fun clicker questions about this topic. So I'm just going to move my head out of the way. Okay, so in which situation would the electromagnetic wave be more successful in inducing a current in the wire? So take a look at both pictures and try to figure that out. Okay, hopefully you've noticed that in this picture on the left, the electric field is lined up with the antenna, whereas here the magnetic field is lined up with the antenna. Right, so does that help you narrow down which electromagnetic wave would induce a current? Okay, so hopefully you've decided that A is the right answer, right? Why is this? We know that charges feel forces in an electric field, right, that are in the direction of the electric field. And so this configuration of the electric field moving up and down would induce a current in the receiver, this receiving antenna. Here's another similar question, so give this some consideration. Okay, so hopefully you've noticed that in this picture, the magnetic field is positioned to move in and out of this loop, and here the electric field is moving in and out of the loop. So in which situation would we have a current induced in the antenna? Would it be here or here? Okay, so hopefully you've decided that the right answer here is also A, right? Why is that? So here we have a changing electric flux. Here we have a changing magnetic flux, right? So I would expect that this changing magnetic flux would induce a current in my loop, and that would be one way of inducing a current in this receiver, right? Using Faraday's law, right? So a changing magnetic flux induces a current. Okay, let's continue. These are just some pictures of antennas, straight antennas and loop antennas. This is a 1930s style radio transmitter, right? Okay, and then finally, we know that radio waves either come as amplitude modulated AM or frequency modulated FM, right? So there's different ways to encode a signal, either in variations in amplitude or variations in frequency, right? But either way, the signal travels by an electromagnetic wave. Okay, so next topic I want to talk about is energy, right? And before we talk about the energy of a wave, let's talk about the energy of an oscillator. So the most useful uh, uh, model of an oscillator that we have is the mass on a spring. And hopefully you remember the formula for the potential energy of a mass on a spring is 1/2 k x squared, where x is the amplitude of that oscillation, right? Or it's x is the distance from the center, and it's constantly moving either to the left or the right of this equilibrium point. Okay, so if I wanted to know the total energy of this oscillator, I could wait until it's at its maximum amplitude, right, demonstrated by this x naught. That would be when the system is entirely in potential energy, right? So no kinetic energy. So one way of quantifying the total energy of an oscillator is in the max amplitude squared, right? So the energy would depend on that max amplitude squared. So this is kind of universal for all waves. So here this is a demonstration of sound waves and how their energy is proportional to the pressure squared, right? So the pressure, remember, sound waves are periodic differences in pressure in air. And so here, if we're plotting the amplitude of pressure over time, I would expect that the energy is proportional to the amplitude squared. Okay, so let's talk about how do we quantify the energy of an electromagnetic wave. And a lot of times, because electromagnetic waves are sort of hard to describe in terms of a single wave, we want to talk more about average energy over time, and average energy over time spread out over an area. And so that's why instead of talking about energy, we more often talk about intensity. So let's describe actually how this is quantified. So the first thing to talk about is we like to relate energy to this vector called the Poynting vector. So Poynting is actually named after a person, but I think it's actually very appropriate because the Poynting vector points in the direction of motion of the electromagnetic wave, right? So the formula for Poynting vector is that it's proportional to electric field crossed with magnetic field, right? So let's all use our right hand, right? Move your thumb in the direction of the first vector, so electric field, and then pointer fingers in the direction of magnetic field, right? So I have pointer in the B field, thumb in the electric field. My middle finger points in the direction of the Poynting vector, right? So we should see this Poynting vector S, pointing in the direction of propagation, right? So it's appropriately named. Okay, turns out that this Poynting vector is a measurement of the energy transferred per unit area. So since electric field is always perpendicular to magnetic field, right, I don't need to write this in terms of sine times an angle. It's just equal to the magnitude of each. And then we also know that electric field is always equal to magnetic field times C. Or actually, here it looks like I did this wrong. It looks like electric field is magnetic field divided by C. No. E is equal to C times B, right? And that means that B is equal to E divided by C. Okay, so this is correct. So you could either write it in terms of the product of E times B, or you could write it as E squared divided by C, right? So this just shows me that I could write the the magnitude of Poynting vector just in terms of electric field squared. Right? So notice what's happening over time is that the magnitude of the electric field oscillates, and so sometimes it's very big, sometimes it's very small. Sometimes it's positive, sometimes it's negative, right? But in terms of electric field squared, we could talk about that being related to the magnitude. But even then, the magnitude is oscillating with time, right? And so this is why we actually prefer to calculate the average Poynting vector. So the average Poynting vector would just be the average value of the electric field squared over time. Notice that that electric magnitude would be going between 0 and 1 times the maximum value, right? Ooh, let me move my head, sorry. I'll move it here. Where will I be out of the way? How about right here? Okay, so the electric field is oscillating between 0 and then a maximum value. The electric field squared is oscillating between 0 and electric field squared. Electric field magnitude squared. So that means that I could just represent the average value by dividing by a half, right? So don't stress out about this too much. If something is oscillating according to a sinusoidal function, we know a sine function goes between +1 and -1. A sine squared function goes between 0 and 1. And so the average value is going to be around a half. Okay, so then let's shift towards understanding what this quantity means. So the average Poynting vector magnitude is going to be equal to the intensity of the electromagnetic wave. So I want to focus on what intensity means. So intensity has a more general meaning, and it's the power per unit area, right? Okay, so I think my next few slides will all be about intensity. Let's move on. But before I talk about intensity, I just want to organize our thoughts about how light can be both described as a wave and a particle, right? So this, now I can move my head back down. Right, so wave-particle duality. So I have the columns here representing, the classical description of what a wave is, and then the quantum description of what a wave is. So our classical idea of a wave is that it is an electromagnetic wave, like we've been discussing. The quantum picture is that light is a photon. How do we describe the energy and momentum of a wave? It's all in terms of the amplitude of the electric field, right? And and that we can quantify the direction of motion of energy using this Poynting vector, and that we can calculate the average energy per unit time per unit area using the magnitude of the electric field squared. So the quantum description of energy and momentum of light is very, very different. So the energy of a photon is proportional to frequency. So this is energy of a photon is h times f, where h is called Planck's constant. We can also talk about a photon having momentum, and this is also related to energy, the energy of the photon. And so you might be asking yourself, so which one is right? The wave description or the photon description? And the answer is both are correct, right? So throughout scientific history, there was this big debate about light being a particle or light being a wave. It wasn't until the early 20th century that we began doing experiments to try to uncover the truth. The truth is that light is both a wave and a particle, right? And under certain experimental conditions, you would see that light behaves like a particle. Under certain experimental conditions, light will behave like a wave. And both descriptions are very useful scientifically, right? So remember when we were looking at the spectrum, the electromagnetic spectrum, we saw very high frequency end of the spectrum and very low frequency end of the spectrum. We know that gamma rays and X-rays have a much different impact on matter than radio waves and microwaves, right? And that's because the photon energy for gamma rays and X-rays is very large, right? Because these are higher frequency photons, which means that they have a greater ability to ionize matter, right? So that's really, really important for understanding human health, is knowing the implications of how those photons interact with matter. On the other hand, we have this description of intensity of light being proportional to electric field squared. This is also very true about light. Okay, so I'm going to continue. Here I have a couple of pictures. This is it's called a Crookes radiometer, or another way to describe it is a light mill. So this is a kind of a pinwheel where one side of each blade is painted black and the other side is painted silver. And it's in this vacuum sealed bulb. And you can see that exposing this to light, you would see the windmill spinning, right? And it's spinning because of the different impact that photons have with one side of the blade versus the other. This is a picture of a solar sail. So this is, things that are being developed by, astronomical engineers, that they want to find ways of, using the sun's light to actually propel satellites and things like that. So this is, an area of development that's very interesting. My own particular field, biophysics, there's a really, really interesting application of using light to understand how molecules and very small biological systems work. So here, these red beams are representing lasers, and the laser has been adjusted using lenses to be in a particular shape. And what happens when we put a dielectric bead, so a plastic bead, in this laser beam, is that it kind of acts like a tweezer. So we call these optical tweezers because we can trap very, very small spheres. Here it says it's a latex sphere. It gets trapped because of the way the laser beam interacts with the sphere. But the really useful thing about trapping these plastic spheres is we can attach them to molecules. So here we have a very interesting system, kinesin and microtubules. So what you see is this is how small packages get delivered in a cell, is we have this network of microtubules, and we have this molecule called kinesin that actually acts as a delivery mechanism, and it walks along the microtubule. So by attaching a kinesin molecule to a bead and then watching it walk along the length of a microtubule, we can see sort of the pace of that walking as a function of time, because we're monitoring changes in this laser beam. Right? We can do any number of experiment, right? We can monitor things like transcription. We can look at DNA unraveling. We can look at proteins folding and unfolding, all using optical tweezers. Okay, so let's continue. I want to talk about more about how light intensity travels as a function of distance, right? And in order to think about this, we really need to understand, what's happening when you have a source of an electromagnetic wave. How would that create a wave that's traveling through space? So in 2 dimensions, we can think of this as kind of like a ripple in a pond. So if you drop a pebble in a pond, it's going to create ripples that look like circles. What would that look like in 3D? We would imagine, a sphere that is growing spatially, right? So, the energy that is released in every, part of this wave, it actually has to expand as it's getting further and further away, right? And so this is, a description of why the intensity of a wave needs to drop off as a function of distance. And that makes sense, right? If I turn on my stereo, it's going to be very, very loud. If I put my ear close to the stereo, it's going to be less loud as I move further and further away. Okay, so if a source of a wave is emitting, if this wave is being emitted in 3 dimensions, then we can think of this spherical wave as getting bigger and bigger as a function of time, and that impacts how we quantify intensity, right? Because remember, intensity is power per unit area. Power is energy per unit time, right? So I would expect intensity to have units of watts per square meter, right? But what is the surface area? The sphere, so this is the formula for the surface area. The sphere, it's 4 pi r squared, right? So it's a little different from a circle. The area of a circle is pi r squared. The surface area of a sphere is 4 pi r squared. Right? So this gives me a formula for intensity as a function of distance, right? So if the power source is constant, I would expect the intensity to drop off as a function of r squared. So keep this in mind. There's actually an aspect of Lab 9 that deals with this formula. Okay, so this is a really interesting problem. So it's saying that we're looking at solar panels, right? So I have a solar panel on planet Earth. The distance from the sun to the Earth is given 1.5 times 10 to the 11 meters. And we also know the luminous power from the sun is 3 times 10 to the 26th watts. So it's asking, what is the power collected on a 5 meter square solar panel, assuming efficiency is perfect? Really interesting problem. So we actually want to solve this equation. Intensity is power per area. We want to solve it for power. So power is going to be intensity times area. But the question here is, what area do we need and where do we use it, right? because I could think of two areas being relevant. One would be this 5 square meters, so the area of the solar panel. But we also know that the intensity of light that reaches planet Earth, it basically needs to be uniformly distributed all the way around the sun at a distance that is the same distance as between the sun and the Earth, right? So that's why I have this kind of imaginary sphere drawn around the sun that is a distance r away, right? So I could use that fact to calculate the intensity of light on planet Earth, right? So the intensity of light on planet Earth would be this power, the power of the sun, divided by 4 pi r squared, where r is this distance, right? 1.5 times 10 to the 11. Okay, so that gives me the intensity of light on planet Earth. How would I then calculate the power collected by the solar panel? Then I could rearrange this formula. Intensity times area gives me power to calculate the power on the solar panel. So why don't you try that process and pause and then check back to see that you get the right answer. Okay, if you're joining back, this is my solution. So the power on the panel is going to be equal to the intensity from the sun on planet Earth times the area of the panel. But the intensity of the sun on planet Earth is equal to the power of the sun divided by this total area. And that total area that I mean is the surface area of an imaginary sphere that encloses the Earth. That is this, where the sphere is has a radius of the distance from the sun to the Earth. Right? Okay, so my answer is 6.79 kilowatts. Cool. Okay, let's continue. Okay, so now we're shifting gears and we're talking about polarization. So polarization is the other topic in Lab 9. And so definitely use this section to understand what's going on in Lab 9. I think it's part B of Lab 9. Okay, so the reason why I have a picture of sunglasses here is that sunglasses are polarizers, and we first need to describe what is a polarizer. And then another place you see polarizers are with fancy cameras. So here we have the kind of filter that you put on a camera. And what we're doing here is we have two polarizers, and you're rotating one relative to another, right? So as you're rotating one polarizer relative to another, we see that light basically disappears, right? So we go from allowing light to pass through to not allowing it to pass through at all. And that's what's happening in both of these pictures, right? So we have a bottom filter, we have a top filter. We're rotating the top relative to the bottom. Okay, so the way that we want to think about unpolarized light, so in terms of what we mean by unpolarized light, we're going to mean light where the electric field can basically point in all directions, right? So remember, our picture of an electromagnetic wave is something where the electric field, oscillates in one plane, magnetic field oscillates in the other as it's moving forward in space. So unpolarized light, or light coming from the sun, we would expect it to have completely randomly oriented electric fields, right? And that's what this picture is representing. So a bunch of different light. Each light has an electric field that is oriented in a different direction. And we can refer to the plane of polarization to be the plane of the electric field, right? So we're doing everything in terms of electric field for this. So it says most light sources produce unpolarized light emitted by atomic motions, and so they are naturally in randomly distributed directions. And this is a demonstration of vertically polarized light, right? So I have the electric field oscillating in the y direction. Here I have horizontally polarized light, so I have the electric field in the z direction. Okay, so what is a polarizer? So a polarizer is going to be a material where we have a bunch of polymers, and polymers are like molecules that are very long, and these polymers have been manufactured to all orient in the same direction. And so you can think of a polarizer as basically being kind of a fence, right, where I have a bunch of molecules that are all pointing in a very straight line. Okay, so what's going to happen when I send unpolarized light through a polarizing sheet? Only the direction of only the electric field that is aligned up with the polarizing sheet goes through, right? So let me try that again. So I have electric fields pointing in all random directions. The light that actually passes through the filter is only the light where the axis of polarization of that light lines up with the axis of the polarizing sheet here. Okay, so if we're thinking of the intensity as being demonstrated by this formula that we had before, so that it's proportional to the magnitude of the electric field squared, we can use this calculation to calculate what would be the intensity of light that passes through the polarizer, right? So we have some sort of initial intensity of the unpolarized light. I want to know what is the intensity of light after it passes through. So if we think of the electric field as being randomly oriented in all directions, right, we can write the direction of the electric field in the y direction as being a component of the total electric field times the cosine of the angle theta, right? So theta would be sort of the angle that the electric field is oriented relative to the vertical. And so if I want the component of the electric field that is in the vertical direction, then I could break it up using SOHCAHTOA and get that the component of the electric field in the y direction is equal to the total electric field times the cosine of the angle theta. Right, so here's a demonstration of that happening. So here I have my vertical axis is y, and this is the axis of the polarizer. I have some randomly oriented electric field, right? So it's oriented at an angle theta relative to the vertical. I want to pick out just the component of that electric field in the y direction, which means that I need to multiply E naught by cosine theta, right? So only the component of E in the direction of the axis is going to filter through the polarizer. So that's how it's going to work. So the first step is what happens if I send unpolarized light through a polarizer. So this is kind of a symbol representing unpolarized light. What would be the intensity of light that passes through? So exactly a half of the intensity would pass through. So I just want to calculate why that happens. So again, the intensity of light before it passes through the filter is given by I naught, which is represented by C epsilon naught over 2 times E naught squared. The intensity of light that results when polarized light is filtered through a polarizer. This is given by something called Malice's law. Okay, so this actually is not unpolarized light. This is light that's already polarized. What would be the intensity when it passes through a second polarizer, right? So now I have unpolarized light coming through. Then I have a polarizer. So now I have light that's polarized in one direction. So if you try to pass it through a polarizer that is perpendicular, then you would get no light through, right? So, so that's what this is demonstrating. I can get light to become polarized by filtering it through a polarizer, but then if I rotate everything so that now I want it to pass through a polarizer that is oriented in the perpendicular direction, I would actually expect no light to pass through. Okay, so then if the amount of light, the amount of the electric field that passes through from one polarizer to another is only represented by the component of the electric field in the y direction, then I need to replace this intensity with E naught times cosine of theta. And I can rewrite this in terms of I naught because the E naught squared times this coefficient gives me I naught. And so that would mean that the intensity of light that's transmitted is equal to the initial intensity times cosine squared of theta, where theta is the angle between them. So now we can see whether this should work. So now I send unpolarized light through a first polarizer. Now I have an electric field that's polarized vertically. So what if I now send it through a polarizer that is oriented at an angle of theta is 90 degrees? So now I need to multiply it by the cosine of 90 degrees squared. Cosine of 90 is 0. So I would expect if I have two polarizers where one is oriented vertically, the other one's oriented horizontally, I would expect no light to pass through. Okay, so this formula here is actually demonstrating why unpolarized light would have its intensity cut in half. So unpolarized light, I really need to take the average value of cosine squared across all angles, right? So this is if I have a polarizer that's vertical, I'm sending an unpolarized light, I really need the average value of cosine squared when I go through a polarizer to calculate the intensity of the transmitted light. So the average value of cosine squared over one period from 0 to 2 pi, it looks like it's equal to 4 pi, or no, it's equal to pi. And then you have to divide by 1 over 2 pi to get, this is how you would calculate average value. So this quantity gives me a half, right? So, so that's explaining why sending unpolarized light through a polarizer would cut the intensity in half. So here, this is demonstrating Malice's law. So here I have the orientation of the polarizer is demonstrated with this red line. So if I have the two red lines lined up together, then the angle theta would be 0, right? So I would expect light to just pass through both filters. Here I have the angle theta is 45 degrees because the relative angle between these two red lines is 45 degrees. I still get some light to pass through, but it's probably less than the light that I get here, right? And then finally, now I have one polarizer is vertical, the other polarizer is horizontal, I should get that this angle theta is 90 degrees, but the cosine of 90 degrees is 0. And so no light is passing through this polarizing lens. Okay, let's do some more examples. Okay, just need to move this over here. Okay, so this is demonstrating, over here I have unpolarized light. I have an initial intensity I0. I'm passing it through one filter. The intensity in this location should be I sub 1. And then I'm passing it through another filter, and the intensity here we'll call I sub 2. Okay, so in this situation, I have two polarizers that are parallel to each other, right? So I can see that the axis of polarization of the two polarizers is lined up side by side, parallel. So it's asking what would be the intensity of light I2 in this situation. Okay, hopefully you can see that the answer is B. Okay, so let's see why. So we have this rule that when unpolarized light passes through a polarizer, the intensity gets cut in half. And then I have I1 intensity going through a second polarizer, but here I have the relative angle between the two polarizers is 0. The cosine of 0 is 1, and so therefore I1 and I2 are the same thing. So that's why you would get intensity 2 is just half of the initial intensity. Okay, let's try another situation. So go ahead and try this problem out and see if you understand. Oh, I think maybe my head was obstructing this solution, so I just want to move my head out of the way. Okay, so now let's try the second problem. So now the only difference between this problem and the previous one is now I've rotated this angle by 60 degrees. Right? So I've rotated the second polarizer. So go ahead and try to figure out what would be the new I2. Okay, if you're joining back, we know that I1 is just going to be a half of I0, so same as before. But now we need to calculate what would I2 be. We're going to use Malice's law. So Malice's law tells me that that I2 should be equal to I1 times the cosine of 60 degrees squared. So the cosine of 60 degrees is actually a half. So cosine of 60 squared would actually be a quarter. And I need to combine that with the original 1/2. So you should get that the answer is C. Right? So I have I1 is equal to I0 divided by 2. I get I2 is equal to I1 cosine squared theta. This is Malice's law. So it's telling me the intensity of light here is equal to the intensity of light here times the cosine of this angle. The cosine of 60 is a half, and so I2 will be a quarter of I1, but it's also an eighth of I0. So the intensity got cut by an eighth in going from here to here. Okay, so now let's try, this is an interesting scenario. So it's saying the figure shows 4 pairs of polarizing sheets seen face on. Each pair is mounted in the path of initially unpolarized light. The polarizing direction of each sheet, indicated by the dashed line, is referenced to either a horizontal x-axis or a vertical y-axis. Rank the pairs according to the fraction of the initial intensity that they pass greatest first. Okay, So we want to rank the intensity of light passing through two filters. So 1, 2, 1, 2, 1, 2, 1, 2. We want to rank who has the biggest intensity versus who has the smallest intensity. So go ahead and try this problem on your own by pausing the presentation. Okay, so let's first talk about this part A. So it's saying that I'm 30 degrees from the vertical here, and I'm 60 degrees from the horizontal here. But this is kind of just a tricky way of saying that these two axes are parallel to each other, right? So I would expect to have the maximum amount of intensity through in part A. So I would expect I sub A to be the greatest. Okay, now we need to think about which would be the smallest. So do you see here that this axis is perpendicular to this axis, right? Because I can tell that there's 90-degree angle difference between this axis and this axis. So this would have the smallest intensity pass through. Now let's talk about B and D. So what is the relative angle between, let's look at this one first. So here I'm 30 degrees from the vertical to the left of Y, and here I'm 30 degrees from the vertical to the right of Y. So the relative angle between these two, I would say, is 60 degrees, right? So they're 60 degrees apart, where one is oriented 30 degrees to the right and one is oriented 30 degrees to the left. Let's try this one. So here I have this axis is 60 degrees from the horizontal here, but I also know I'm 30 degrees from the horizontal here, right? So the relative angle between these two is 60 minus 30, so 30 degrees. So in terms of situation B and situation D, which pair is more closely aligned? It would be D, right? Okay, so now let's try to rank intensity. I would say biggest is A, then D, then B, and then finally C. Yay, we got it right. Okay, so let's continue. Here I've worked out the intensity for all four, so you can double check that you understand. Okay, so this is maybe my favorite thing about polarizers, is that we can calculate what happens if we have three polarizers. So, So if I have three polarizers, and specifically I want to make sure that polarizer 1 and polarizer 2 are perpendicular to each other. So I would expect 1 and 2, when I line them up just on their own, I would expect no light to pass through. But here's the tricky thing is, what if I put in between 1 and 2, I put in a polarizer 3, and it's at a 45-degree angle from polarizer 1 and polarizer 2, right? So essentially now I have light going from 1 to 3, where the angle is 45 degrees, and then from 3 to 2, where the angle is 45 degrees. So in this region here, I have three polarizers. I'm actually getting more light to shine through than in this region here, where I only have two polarizers, right? So it's very counterintuitive what's going on. Okay, so if I only have polarizer 1 and 2, I would expect no light to shine through, because initially I'm lined up in the horizontal direction, and then the angle between 1 and 2 is 90 degrees, and so no light shines through. But if you place 3 in between 1 and 2, then the light that comes through polarizer 1 and 3 would be a half of the initial, and then the light that shines through 1, 3, and then 2 would be a quarter the initial, right? So it's very interesting that here I would expect to get light to get cut off by a half and then by a half again, but here I would expect no light to shine through at all. Here's some cute applications of polarizing lenses. So we can use polarizers to make 3D glasses. So in this situation, you have a 3D movie, and the 3D glasses are set up so that your left eye has a polarizer that is vertical, and your right eye has a polarizer that is horizontal. And then the light that is being projected on the screen has some light that is intended for your left eye that is vertically polarized, light that's intended for your right eye that is horizontally polarized. And so you're really only seeing you're seeing a completely different picture in your left eye and your right eye. This mimics the situation of seeing a three-dimensional object in real life, where your left eye and your right eye see slightly different pictures. And so this is how we can mimic 3D onto a 2D screen. Here's another important application. So this is how a laser printer works. So no, this isn't a printer. This is an LCD screen. So LCD stands for liquid crystal display. So a liquid crystal is it's a amorphous solid that has a bunch of molecules that can rotate and move relative to each other, but these molecules are all cylindrically shaped. And what happens is that these cylinders can actually act as polarizers, but here we can basically have different signals for red, green, and blue in a display by changing the orientation of the liquid crystals in each channel. And so this basically controls the color and the intensity of light that is controlled in each pixel of the LCD display. Okay. And this polarization is also really important for photography. So if you ever need to reduce glare in a picture, you could use a polarizing lens. And the reason why is that anytime we have light being reflected off of a surface, so here I have unpolarized light, it turns out that the glare from this reflection is always going to be horizontally polarized because of the way that it interacts with the surface. So if I want to block off that glare, then I need sunglasses or lenses that are vertically polarized, right? So that basically sets the direction of polarization for sunglasses to be vertical, because we want to block off any glare of light that gets reflected off of surfaces in a horizontal way. So these pictures are showing the impact of adding a linear polarizer to block out glare. These are more pictures of the same thing. Right, so here it's demonstrating what happens when you have sunglasses and you rotate them relative to each other. You can mimic that demonstration that we did at the very beginning in talking about polarizers. Okay, so the next part of this lecture is going to be about wave speed. So I'm actually going to stop here and upload this video and continue with the next part later. Okay, thanks very much.